So last time we stopped here in discussing implementation in C++. So we said that in typical C++ code, we start with a bunch of include statements because we include so-called header files, which have some important code in there. Then this statement here specifies that we are using so-called standard template library. And that when we use something for standard template library, we are not going to prepend so-called std dots because we are going to import this into the main namespace, into the current namespace that we are working on. So that's what the statement means. Now, this we specified here a function, just like in Fortran. And we said that we are going to use, take z0 with call by reference for efficiency reason, but we're going to still specify that this is constant in the sense that z0 cannot be changed inside the subroutine, this function, and max steps we're going to call by value because it turns out that this doesn't cost any efficiency degradation. Here we defined z to be a complex number, just like before, but in Fortran. But the difference is that we can specify a complex number on the fly. So when we need it, we define it and initialize at the same time. And this statement doesn't need to appear on the top of the code. It can appear anywhere in the code. So that's the nice thing about C++. You can define your variable anywhere in the C++ code. Now, this is particularly important when we have when you have for loops. So in for loop, you can define the integer counter I inside the loop. So you see, we write integer I is equal to 0, isn't it? So we defined integer I to exist only within this loop, this for loop, and not outside. Now, why is this important? Well, there is some generic rule in programming that you want to have variables as local as possible. So more local the variables, less error prone your code is. So less possibility of mistake. Because if all the variables are global, you're going to sooner or later make a mistake and use variable which has not been properly initialized, and you will not notice you have an error. So the general rule is make variables as local as possible, and therefore it's a good idea to specify those variables only inside the statement that we need them, such as counter in the for loop. Now the for loop starts always with 0 and ends with I less than max steps, and the reason for this kind of syntax in C is that arrays in C start with 0 and they always end with n-1. So if you specify an array that has a size of n, then the wallet entries are a of 0 and to including a n-1, while a of n, of course, is wrong. That doesn't exist. So therefore, that's the rule is that you always use the statement, although it's not mandatory. You could specify this rule differently if you want to. Then the statement z is equal to z squared plus z0. It's the same in all languages, but here the if statement is slightly different. So we say if absolute value of z is bigger than 2, then we return the value. Now, the difference in Fortran and in C++ is that in C++ we need to give a variable after return statement. So return always needs to return a variable in a function, or it needs to return nothing if returns void. So if we return void here, that's one possibility. Void means return nothing. This is like subroutine in Fortran. In this case, then we don't need to return anything here. But otherwise, if we have a type on this side, we need to return the variable of exactly the type that appears here. So basically, this variable here is related to this variable here. They have to match. Otherwise, we're going to get an error. Okay, so if we survive then to the end of the loop, then we return maximum steps, because that means that we are part of this point is part of the Mandelbrot set. and we want to return as big number as possible. Okay, so this is the little function that we wrote, and now we need to specify the main part of the code which calls that function. And again, we're going to make it OpenMP parallel. So the code starts with specifying the dimensions for the x, so the mesh points in the x direction, mesh points in y direction. They're both 1,000 in this case. And notice we use const integer. So this is equivalent to parameter integer in Fortran. So we want to make it constant so that we specify that this variable is not going to be changed within the code. It's not very important in this case, but many times you want to emphasize to the compiler that this is something that you don't want to change. So this is good both for the fact that the compiler will enforce the rule that's not going to be changed in the code. So if you try to change it, there's going to be an error. And at the same time, it's good because this compiler can optimize out such variables which are specified as constant. Now, max steps is going to be 1,000 in this case again. And then here we define an array of that specifies 4 numbers that has to do with the minimum x, maximum y, maximum y. So somehow it's convenient to have an array rather than 4 numbers. And this array has double numbers, of course, so floating point numbers, which are called double. In this case, this double is equivalent to real 8, so it has 8 bytes. There is something in C++ which is called float, and float would be equivalent to real 4 in Fortran, and double is equivalent to double is equivalent to real 8. So which means that double has 8 bytes, float has 4 bytes. Now back to the fact that we specify an array. So it turns out that in C++ you have to specify that this is an array with this brackets here. So the default specification of the array in C++ is first the type, which in this case is double, then the name of the array, such as x, okay, the name that you give to the array, and then it needs to be followed by the size of the array. And this n here has to be constant. It's very important, it has to be constant. So if this n here is not constant, then things might still, the code will work, but it will malfunction. So you can easily have a core dump if you don't specify this thing to be constant. So it's very unfortunate actually that C does not allow dynamic arrays to be done in this way. If you want a dynamic arrays, then you need to use allocation of memory. So in C, you need to use malloc. In C++, you need to use so-called operator new, or you have to use types such as array, such as vector. We're going to use this vector here. So vector, however, is something that does not need to have a fixed constant size. So this nx times ny is not necessarily constant. But if you specify it in this way, it has to be a constant, unfortunately. So this is a C-like arrays which need to have constant. Okay, so now this type of thing defines in C a constant. No, it defines an array with a constant size n, but it doesn't initialize it. And until recently, there was no simple way of initializing C arrays. But they added this syntax relatively recently in one of the recent versions, that if you specify, when you define a curly bracket and some values in there, then this initializes the array. Okay, so basically this means that we are initializing here. Now it turns out that if you initialize an array, then you don't need to specify n. You can if you want to, but you don't need to. Why? Because, well, the compiler can read off how many variables are in the initial list, and it will adjust n appropriately. Yes, you have.
So besides the size difference, are there any other differences between a double and a float, and why is it better to use one instead of the other in certain situations?
Yes, so the fundamental difference is in size, as you said. One has only 4 bytes, the other has 8 bytes, and the issue with using 4 bytes is that it has precision, I think 10 to the minus 6, if I'm not mistaken. So the double number, for the double numbers, if you have double x, for example, then if you do something like x plus 10 to the minus 16, it will not be equal. No, let's say you have 1. This is important thing is 1. So if you do 1 plus 10 to the minus 16, and x is a double number, so well, that's what I want to say. Let's say that you say x is equal to 1 plus 10 to the minus 16, for example. This is not equal to 1 for the double number, okay? And if you write 1 plus 10 to the minus 17, then this is equal to 1 because of precision. So the so-called error of the double number is 10 to the minus 16. Actually, it's 2 10 to the minus 16. Well, actually, I'm not so sure if 10 to the minus 16 will work. I think the error is 2 10 to the minus 16. But 10 to the minus 15 will definitely work. Okay, but if x is float, let's say the f is float, then this error is basically, I think it's around 10 to the minus 16, if I'm not mistaken. So 1 plus 10 to the minus 6, 10 to the minus 6 is already equal to 1. So in other words, there are not many digits that you have. I mean, if you have a number 1 point something, there are only 6 digits that you can rely on. All the rest are wrong, okay? So this is not much for modern algorithms. Very few are actually written with floats. Of course, if you are absolutely sure that that the algorithm is stable enough that you can use only 6 digits, then you can still use floats. For example, on GPUs, the floats are way faster than doubles. GPUs actually support floats mostly, and well, they have doubles, but you're penalized. I think the speed is like 2 or 3 times lower if you use doubles. Now in CPUs, I don't think that's such a big difference. So therefore, I always use doubles. You're not penalized much by using doubles, except that the memory, you use a little bit more memory. But in GPUs, it's actually a big difference. So if you have a very stable algorithm, maybe still okay to use, so maybe it's advisable to use floats. Yeah, you have to be careful about error accumulation so much more. It's so easy to accumulate error. Yeah, so what I wanted to explain here is that we have here an array of doubles, and we did not specify here the dimension, although normally this would be mandatory, but because we have an suggestion list, this can be skipped. Okay, so then next is this statement here, vector. So I mentioned last time that C++ does not have a standard way of specifying multi-dimensional arrays. So still they do not have support for multi-dimensional arrays. So what we are going to use, however, is one-dimensional array. And of course, one-dimensional array can always be faked into multi-dimensional arrays with a little bit of extra code. Okay, so we're going to use one-dimensional array, and this is called vector. And so vector is a template, which means that it can contain any types you want. So I could specify here doubles or integers or anything. So currently integer is enough, sufficient, so we're going to use integers, but I mean, we could specify here doubles, and we have then one-dimensional array of doubles. And then this is the name that I give to the array, mand, and then this has to be followed by the size of the array. And this number here does not need to be constant. So basically I can specify here that nx times, that basically the nx is, let's say, dynamically read from the file. or it's determined here to being, I don't know, tangents hyperbolicus of some number, and then I make integer out of it, for example. I'm just coming up with some crazy function, let's say, and I calculate on the fly how big this number is, and then I can allocate the array of that size. That will work. So in other words, this means that the array has a dynamic size. It can be determined during the runtime. It's not known before. And of course, that's what we use most of the time, because for most arrays, we don't know how big arrays we will actually eventually need. So this vector is, of course, vector is something that is appears in here. In this include file, we need to have this include file vector, and then we can use the type vector in our code. So this statement actually not only allocates it, basically this statement allocates it. So prepares the memory, but it doesn't set it to any number yet. Doesn't set it to 0 or something. Then this statement here times basically gives you a time, starting time, and in units of clock ticks. So this is actually a C call, and it gives you as a result a type which is called clock T. So this is the type which needs to be clock T. Now, why do we use clock T rather than integer or double? Well, we could use double, would probably work, but what type this return type of clock is depends on the compiler. So sometimes it's integer, sometimes it's a long number, sometimes it's a double number, depends. So in order to be safe, there is a type that is provided, which is called clock T, and this will always work. Okay, so it's a good idea to use clock T rather than double, although I think double will work. Now, this statement here, OMP get W time, means you get whole time what is needed for OpenMP parallel parallel code, as we discussed before. So, and this time I think is in doubles. So therefore we can here initialize double to this starting time. And then we have this double for loop, just like in Fortran, except that of course the loop is specified in C-like fashion. So integer, the counter is defined inside the loop, and it's initialized. It starts with 0. It's initialized to 0. We know that it's going to be less than nx, and this I++ always means in every step you increase I for 1. So I++ is equivalent to I plus equal 1. Okay, so in Python, I++ actually doesn't exist, which is interesting. This is C++ like thing. So in Python, you have to write the same statement as I plus equal 1. This is the same thing. Okay, so then we specify both component x and y as a double numbers, and of course they are obtained as a uniform mesh between these numbers, which are contained in xt0 and xt1, xt2, xt3. Now the two comments are in order here. When you access a C array in C++ or in C, you have to use square brackets. Okay, square brackets. You see the square brackets. The rounded brackets will not work. They have to be square. And that's different from Fortran. Remember, in Fortran, we had to use rounded brackets. Okay, rounded brackets. And C++ we use square brackets. Now in Python, we also use square brackets. Okay, so that's closer to Python in some sense. That's one thing. The other one is that we have to divide, we have to write this division here, not in integer, but in doubles. So let me write you a code which will malfunction. So instead of this I divided by nx minus 1 dot, I could easily write times I divided by nx minus 1. Okay, so that looks syntactically completely correct. An equivalent code. So I'm just removing this dot here. Okay, and it should work, doesn't it? But it turns out it will malfunction. So does anybody know what's going to happen?
So if you put the dot, you're making the one a double, but otherwise it's an int. So the two types don't work together.
Yes, yes. So what's going to happen if you don't put this dot here? Then compiler will say, well, nx is integer, I1 is integer, so this result is integer. Then I is also integer, and then it will decide, well, then we divide integer by integer. I divided by nx minus 1 is integer, and the result will also be an integer. Okay, and because I is always smaller than nx minus 1, this will always be 0, except when I is equal to nx minus 1. In this case, it's going to be 1. Okay, so we're going to have either 0 or 1 as a result. Most of them will be 0. So this is not what you want, isn't it? You want the floating point number. So in order to do the math correctly, you need to either typecast either I into floating point or nx into floating point. Or what is the simplest is typecast 1 into floating point. But, well, the easiest way is then just making this one floating number. So when I specify 1 dot, is I'm saying 1 is now not an integer, but it's a floating point number. So this dot here is the same as saying that it's 1.0 or something. So that saves me in the sense that now, because this one is floating point number, nx minus 1 is also floating point number, and then this division also needs to be in floating point numbers, and then the final result is correct. It's floating point number. Okay, so this is the usual trick when you divide integers. Make sure that at least one of the variables in there is floating point. So you, for example, if you need to divide by nx itself, I usually write I divided by nx plus 0 dot. Okay, and that's sufficient to have right division. The alternative is to write the following. You can typecast into double. So there's called static cast. There's typecast. It's called static cast of double. And then you can typecast I, for example, divided by nx. This will of course work. So this long thing, which is called static cast double, is transforming integer into another type, into double type. So you can always use the static cast, but it's kind of long and complicated. Well, looks like a complicated statement, isn't it? And this typecasting is intentionally being so complicated. I mean, there is a C way of typecasting, which is saying double like this I. Okay, this will also work, but this is kind of discouraged in C++. And the reason for this is because it leads to so many errors. So this typecasting is the place where the most errors occur. And therefore in C++ they decided that such a statement should not be used. It's discouraged, and maybe it's going to be discontinued because that is very, very error prone. So typecasting is supposed to be something that you don't use very often, and it's kind of easy to find in a code. Anyway, too much about typecasting. The important thing is that you want this to be floating point, therefore you create at least one number in there to be floating point, and then it works. Now, the interesting thing is that this is also something that was relevant in Python, but actually only Python 2. In Python 3, they changed. So in Python 2, the behavior was exactly identical. You have to have at least one floating point number. And if you divide two integers, it will be an integer. But in Python 3, they decided that division of two integers will always result in floating point number. Okay, so in Python 3, this issue is over. Okay, so finally, the last statement here is we are invoking here the function Mandelbrot, and we are giving we need to give to this function a complex number that we create here on the fly. This is how you create a complex number on the fly. You specify the type and then initialize it at the same time. So that's how I specify the type and initialize at the same time, complex number, and then we give this max steps as a second argument. And then the result is being written into this one-dimensional array. And this is, of course, the standard way of converting one-dimensional array into something that serves the purpose of two-dimensional arrays, of course, but it's one-dimensional. So ny is the second dimension, I times ny plus j will act like a two-dimensional array, isn't it? But of course, it would be more convenient if there were standard two-dimensional arrays in C++, but they don't exist. So that's the way around. Okay, so finally, then we call once more the clock, which gives you clock ticks. And then we, here this statement calculates the time. And the way it needs to be done is we subtract this end time minus start time, but this resulting thing is in units of clock ticks, which could be either double or can be integer. And because it could be integer, we are actually doing, what do we do? Typecasting to double. Yeah, okay, that's the statement that I was actually claiming before. It's very dangerous, but I'm using it here. So I'm typecasting it to double this difference of the two most probably integer or double, depends on the compiler. And then we have to divide this per clocks per second. So this is a variable that is defined inside this inside the C time, includes C time, includes this type, okay, clock, and this variable clocks per where are we? This variable clocks per second is number of clock ticks per second. So we have to divide by this in order to get seconds. And of course, get W time gives you seconds. So then it's easy to just take the difference and we know the time. Now, finally, this statement here prints result into the standard output. Well, actually not exactly standard output, it's called standard error output. So it turns out that there are three different standard outputs that you can use in C. One is called C log, one is called C error, and one is called C out. C out. So C error, C log, and C out. These are the three standard outputs. Now C out is so-called standard output to the screen, which can be redirected with sign greater, just with sign greater. So when I do something like this, month C, and I don't know if you see this part. So if I do month C and redirect into some file, then I'm redirecting with this symbol here, I'm redirecting C out. Okay, but if I and in this case, the C log and C error will still be displayed on the terminal. But if I do this, 2 goes to address of 1, then I force both C log and C error to also print to the file. Okay, so all the executables on a Linux-like systems, including Mac system, have 2 ways of printing to the screen. One is to printing to the standard output, and the other one is printing to the standard error or log output. So, and the difference between the two, fundamental difference, is that this log and C error doesn't buffer, as I explained last time. So buffering means it does not, it immediately displays the result on the screen once it's being invoked, while C out does not immediately displays the result on the output, but it kind of buffers it. When a sufficient number of strings is being thrown on the stream, then it actually displays them. Okay, so therefore we decided that we're going to write to the C out the real results that we're going to plot, and to C log we're going to only just print the time. And so the printing in C++ is a little different than in most other languages. We need to use this double lesser thing, which basically the way you should think of it is that you're throwing something into this type, and this type is called stream or output stream. So this has name output stream, and this is an operator with which you throw something on that stream. And throwing on the stream means if you throw a string on the stream, it means string is going to be printed. If you throw integer on the stream, integer will be printed. If you throw double number, double is going to be printed. If you have your own type, you can throw that type into the stream, and this type is going to be printed. That's the philosophy. Okay. So this is a string, C++ string with double quotation marks. Single quotation marks in C, it's not a string. That's very important. So the single quotation mark in C, you can only specify one character. If you specify AA and just single quotation mark, this is going to be this will be equivalent to only one character, not two. So a string cannot be contained within single quotation marks. Yeah, double quotation marks are fine for strings. So we throw this string, then we throw a double number, then we throw another string, then we throw another string, then we throw another double number. Oops, I'm not showing this, huh? We throw another double number, and then finally we end the line with something which is called ENDL. Okay, ENDL. ENDL is actually equivalent to saying that that we are throwing in /n. Okay, /n is a standard code for new line. Okay, so throwing, oops, it has to be in double quotation marks. So throwing /n to the stream is the same as ENDL, which means ending the line. So go to the new line. Okay, so but in C++ we always use this ENDL as a standard way of ending the line. Yeah, in Python we never use this thing. By default, the way print statement works in Python is that it will always, every print statement will append a kind of new line by itself. So you never do that because it's done by default. Now, yeah, so this is the printing of the time, and then we have two more loops here, two standard loops. We recompute this x and y because for speed it's better to recompute than store, and then we print out. This kind we use cout. We print x, y, and in this case 1 divided by the number of iterations, so that whatever is in the Mandelbrot set is a very small number. And we need to add this ENDL for the new line. Okay, so that's all there is to it. That's the entire code. Now, how do we compile this code? Well, I can do just make, and I will see how the compile directive works. So the right compile directive in this case is is the name of the compiler. So the old name of the compiler was G++ -10. I think the new compiler that I have currently is G++ -11. Then -03 is the optimization, just like in Fortran, maximum optimization. -f_openmp means that we are using this openmp parallelization. Then -o has to be followed by the name of the output file. And then finally, we give the name of the input file that we are compiling. And that works. And it produces the output file mont_c. And then, of course, I can do mont_c and then pipe this into some file that I call mont_d.dat. And I see that the time that this needs, clock time is 1.5 seconds, but hold time is 0.2 seconds only. Now for the Fortran code, I do the same, and I get a very similar number, 1.5 versus 0.26. So this is, of course, subject of a slight error. So if I run it many times, I can get some average number. But as you can see, that wall time is of the order of 0.26 to 0.27 for Fortran, and for C is actually extremely close, 2.66, 2.74, and so on. So which one should we expect to be faster, Fortran or C?
I'm pretty sure Fortran's supposed to be faster, right?
Yes, yes. It's supposed to be slightly faster, isn't it? And the reason for this is because Fortran does not use pointers. I mean, it has its own pointers, but these pointers are different. So every other language, C, C++, and all these languages, including Python, of course, but all other languages use some type which is kind of pointer. And the issue with these pointers is that two different pointers can point in the same location. So every time that you change a variable somewhere in memory, potentially this could mean that several different variables are changed because several different pointers point to the same location in memory. And this issue is called aliasing. So, and it's a complicated engineering problem that you need to solve when you try to find which variables are changed when you change something, okay? And that usually leads to performance degradation. And all combining languages except Fortran have this issue of aliasing. So we could have a type where two different variables share the same location. So Fortran is expected to be slightly faster in very, let's say, good implementation. But this this difference is small in modern compilers, at most 10 to 20%. And second, actually, G-Fortran does not have this advantage, because the way G-Fortran works is that it compiles the Fortran code into C code and then C into objects, into the executables. Because the C code is intermediate code, it does not solve the fundamental problem of aliasing. So if you use Intel Fortran compiler, this one is the real Fortran compiler, in the sense that Fortran is directly compiled into an executable and an assembler, and therefore you could gain a little speed, extra speed in Intel Fortran compiler. But the speed, the change, the difference is not so large anymore that it would be really important. So the first approximation, we don't care about this little performance. Unfortunately, of course, we know that the coding in Fortran is much harder. So I mean, it's much more error prone, let's say. So therefore, I am a firm believer that other advanced codes probably have an advantage over Fortran. Okay, but so now we have the data, and we want to display now the results. We have results are in month d.dot, and we said that the way to do it is to use gnuplot gnu.sh, and that will display the result. Unfortunately, displaying the result already takes some time because gnuplot is not terribly fast. Yeah, but it looks okay when we display. Okay, so one thing that I want to mention here is that I used makefile to kind of do the compilation efficiently and conveniently. And for this, we need to know just a little bit about makefile. I will return to this makefiles a little bit later, but for now, I will give you a very, very short introduction into makefiles. So makefiles are a way of storing the compiling directives in a file. Of course, you could just have a text file that stores these directives, but that wouldn't be efficient. So the nice thing about Makefile is that these rules are evaluated only when needed. So let me explain this. So if you have a very large project which has hundreds of different files, and the compilation of such project takes sometimes hours, and then let's say that you make a small change in such a project. I mean, you're changing the code a little bit. You make one statement difference. Then you don't want to wait an hour to compile the entire thing. What you want is to compile only the parts which need to be recompiled. Okay, and when you use Makefile, you can achieve that. You can write rules in such a way that only the files which have been changed recently are recompiled. So this Makefile will always look at on the left of the rule and right of the rule, and it will say if the stuff on the right of the rule, in this case, for example, month c.cc is newer than month c on the left of the rule, then I'm executing the rule. Otherwise, I'm not. Okay, so that's the power of Makefile. Makefile always looks at the left of the rule and right of the rule, and depending on which one is newer, which file is newer, which file has been touched at a later time, it will either execute this thing or will not execute it. And of course, that's very powerful, because then you have a complicated project. For each file, it will be decided whether it needs to be recompiled or doesn't need to be recompiled. Okay. Of course, every time it needs to be linked, but it does need to be compiled. Compilation takes most of the time. Okay, so now on the top of the Makefile, we usually specify some variables. It can be any variables, but in this case, I just specified variables for compilers, C++ and F90 for compilers. Now, these values of CC and F90 are useful to specify, but even if you don't specify them, they might be given on your system. So let's say that I don't specify them, so I commented them out, and I can still try to type, okay, I can make clean, and I can type make. And you see that that actually C++ was named G++ now. So where is this information coming from? So I didn't specify here anything for CC, and well, here I'm using CC, and this CC was becoming G++. Where is this coming from? This information. So there are several rules. The way make works is that it could be a default. It could be an environmental variable. For example, I have specified here that CC is an environmental variable that's called G++. I can write that CC is going to be G++ minus 11 and recompile again. And you see now I'm using G++ 11. So clearly the way Makefile works is that it takes these variables, it looks at these variables on the, if they are not specified inside the file, it looks at the system and into the Unix system, and it checks whether they are defined there. And if they are not defined even on Unix, then it takes some default variables, default values, which usually are empty. But if they are, but for some, for example, CC, I think even default is not empty. So these variables, the first approximation, they need to be defined inside the Makefile. But if they are not, then there might be some default values on your system. That's all I want to say. Okay, so anyway, these are some variables. And then the way you use the variables in Makefile is to write $ rounded brackets, CC. So that's how the variables need to be invoked. So specified without $, and used when we need to use $. And then the way the Makefile works is that you have a set of rules. So every rule that appears blue here is a rule. So all is a rule, month C is the rule, month F is the rule, and clean is the rule. And if from the shell, when I type make, I can invoke any of the rules. I can invoke clean, I can invoke mandf, mandc, and all. So for example, make clean will invoke the clean rule. Make mandc will just invoke mandc rule. Mandf will invoke mandf rule. But if I do make and I give no rule, then what happens is that the first rule is being invoked. Okay, so that's how the make file works. So if you specify nothing, then the first rule is being invoked. Now the first rule here is called all, and it actually invokes mandc and mandf, and it does actually absolutely nothing for that particular rule. That's how this you have to think of it. So in order to get all, what we need is mandc and mandf, and then the system, the makefile works recursively. So it says, okay, do I have mandc? Well, I don't have mandc. Do I have mandf? I don't have mandf. If I don't have it, then I need to search for a rule, and maybe I find it. And well, yes, of course, the rule exists, mandc rule exists, so this has to be invoked. And then of course, mandf has to be invoked. And then it says, on the left, I have mandc, on the right, I have man.cc. Does man.cc exists? If man.cc did not exist, then there should be another rule to create manc.cc, okay? But manc.cc exists. It's actually a file that exists on the source on the directory. So therefore, now I'm done. I have everything I need, and then this is actually an execution statement that can be executed when I have everything that I need on the top. Okay, and so this is an execution statement which needs to be here prepended by a tab. So this thing here is not allowed to be spaces. It looks like space, but it's not a space. Space will not work. It needs to be actually a tab. And so this, after the tab, there is a real compilation directive, something that needs to be executed on the system. And this thing says, well, invoke this variable cc, which in this case is G++11. Then we specify -0 3 -0 openmp for openmp invocation. Of course, I could specify something which is called C flags, and I could put in here -0 3 and -f openmp. So actually, this is much more standard to have something which is called C flags. And then I could use here, instead of this, I could use C flags. This would be equivalent. And then I can use, for example, here also C flags if I want to. Okay, this will work in exactly the same way. But F openmp is also in C flag, so I don't need it there, for example. And then -O is a directive which says after that -O option, we need to specify the output file. And this strange variable here, $@ means take the string on the left-hand side of the rule, which is mandc in this case. So this is kind of a short, well, it's kind of, it helps you to make your makefile more compact. So instead of writing this mandc twice here and also here, I can use this special variable, which is $@ that takes whatever is on the left-hand side of the rule. And then this $lesser takes whatever is on the right-hand side of the rule. Actually, it's not exactly everything on the right-hand side, but the last one on the right-hand side, but this is a little bit too details now. So anyway, these two variables are kind of something that is on the left of the rule and right of the rule is being taken in this case. And of course, this works the way it's supposed to. And then the clean is another rule, as we said, and clean means you remove everything that you create during the compilation. That's the usual rule, what you need to do. And I will remove now -f means with force. So even if the system would like to ask you, are you sure that you want to remove? I'm definitely going to force it. So -f. And so I will specify all the executables that were created. So usual story is that if you want to if you go to a new computer, you copy everything to new computer, you have to do make clean first, because you want to remove all the compilation from some other place, from some other compiler or some other system, and then you create make, and then this will go through all the it will create, it will do the rule all. Usually all is the first rule in makefile, and we create everything that we need. Okay, so that's a very short intro into the makefile. I plan to come back to the makefiles at some future date soon. But for now, this is like a very short intro that tells you a little bit why these makefiles are useful. So is there any question about makefiles? No? We will return to this, so it should be okay. Okay, so next language that I usually presented, but I don't want to do it today, is Perl. Now, Perl used to be, I mean, I used it mostly for so-called regular expressions, because C, for example, doesn't have regular expressions, and they're very useful. But right now, Python has almost everything that we need from Perl, so I usually skip this. I keep it just for comparison. For example, we will see that the speed in Perl is unbelievably worse than even in Python. So Perl is interpreter just like Python, but it's way slower interpreter than Python. I mean, unbelievably slower. So even in terms of interpreters, it loses. So therefore, I usually skip it. And then finally, Python. This, of course, is going to be bread and butter for us. We're going to use this most of the time. So of course the code is going to be way slower than in C++ and Fortran, because Python is interpreter, but nevertheless it's still one of the fastest interpreters in the market. And of course, because it's interpreter, it's much more easy to code in it. There are many things which are kind of dynamically done properly, and it's just so much easier. Okay, so what do we do in Python? So we're going to use here this directive from SkyPy import star. So we're going to go into details of what this actually means, but for now, just think of SkyPy as being the library, basically module, which includes all scientific code, and some of this we're going to use here. Actually, I think in this case, NumPy would be enough. We could just include from NumPy import star, and we were going to import everything to our working module. So this means the star here. And then we are going to use also pylab. So pylab is actually matplotlib, which is for plotting. So pylab is something that we use for plotting, and we're going to also import it here. And then we're going to import time, not with a star. So we could also, of course, write from time import star, but we're not going to do that. We're just going to import time. Why? Because from time we need only one thing, which is time, nothing else. While usually, at least in most of scientific codes, we need a lot of stuff from SkyPy. For example, I mean, pi is a number that we need. Tangents, sine, exponent, everything is defined in these libraries, and without that, there's nothing. None of those symbols exist. Yeah, but I mean, in this case, I think NumPy is enough. I was exaggerating with SkyPy. So the way it usually works is that if you include SkyPy, SkyPy will include NumPy as well. But it's probably too much right now. Yeah, so this is the function that does the same thing as the one in C, mand. I'm going to call it mand rather than mandel, but the same thing. So the input is the complex number z0 and integer max steps. So as you can see in Python, we don't specify what type z0 is. Okay, so why not? Well, it turns out that in Python, we don't need to specify types at all. We never specify type. So Python being interpreter, has variables which are auto-typed. They're called auto-typed, which means that variable will have a type as necessary at the moment. So here it might not be specified at all. Then later on, when we start using Z0, it might become complex. It might change during the execution and become integer. Then it might change and become double. Then it might change and become complex again. So the type will change depending on the statements. Okay, and that of course is possible only in interpreters. That doesn't work in compilers, but it's of course very convenient. So Z0 will probably be complex because we are gonna call it with creating complex number. So therefore, when this execution occurs, Z0 is going to be complex. Now Z here, we're going to also force Python to use complex from the very beginning. So this statement here, Z equal to something, means of course that we are kind of defining that Z exists, or we setting it to 0 at the beginning, but it's not set to floating point number 0, but it's set to complex number 0J. This J is imaginary unit, isn't it? And specifying 0J is like saying, make it complex and make it 0. Okay, so we're setting Z to complex 0. And then we use this for loop in Python, which has exactly the same effect as for loop in C++. So because range is something that gives you numbers between 0 and max steps minus 1. Okay, so this range is something that gives you, that start with 0 and up to max steps minus 1. So the range actually, it used to be just a simple array. So the way iteration work in Python is that we always iterate over some object. Typically it was a list. And so range would create a list. So in Python 2, for example, if you specify something like range of 10, it will give you a list from 0 to 9. But in Python 3, it actually doesn't do that anymore. So in Python 3, it gives you output as an object range. And the reason for this is because this is kind of more efficient. We use range many, many times. And we actually, it's kind of, let's say it's too inefficient to create a list every time. So, but nevertheless, if you want to see what range really is, you can typecast it into the list object. And then you can see that the list is actually has integers from 0 to 9. So again, in Python 2, even without typecasting, range would always result in a list, because fundamentally you can think of it as being a list from 0 to 9. Yeah, so basically we're now iterating over all these numbers from 0 to max steps minus 1, as in C. Then we say if absolute value of Z is bigger than 2, then we can return this iteration number, just like in C. But notice that there is one fundamental difference. In C, you always need to end the statement with the semicolon. Okay, so in C, if you don't put semicolon, then this doesn't mean that, this means the statement is not ended. And you always need to start the statement by this curly brackets. Okay, that's in C or C++. Curly brackets and semicolon. Without this, things don't work. Now, the philosophy in Python is very different. So Python gets rid of this curly brackets by saying that statement is defined by so-called justification. So it's very, very important how the code is justified in Python. So if it's justified, like everything that is justified in the same way is part of the one statement, and this thing is another statement, isn't it? So therefore, justification is essential in Python. If you don't justify things correctly, there's going to be an error. Now in C, justification is completely irrelevant. You can have the entire thing in one line, and the statement doesn't change. of course, therefore, you need to have this curly brackets and semicolons. Now, again, in Python, the idea is just use justification for defining beginning and end of statement. So new line always means equivalent to having a semicolon at the end. Okay, because we go to new line, that means it's a new it's a new command. So justification is enough. And one more thing that is kind of interesting is that in if statement does not need curly brackets. So in C++, you always need to write if, and then the statement has to be in curly brackets. Now, the curly brackets in Fortran, in Python are okay. You could use curly brackets if you want to. It doesn't change anything, but are not essential. So you can skip them and it still works. The other thing which is very important is that all statements, such as for statement, needs to end with this double dot, and if statement needs to end with double dot, because that means that something has to follow that thing. So for statement ends with double dot because there is a statement that has to be evaluated inside the for loop. Okay, so this always means something needs to be under that for loop that is being specified, doesn't it? So it's kind of obvious. So for loop requires some specification, therefore we have to write this double dot here. And similar if requires some specification after that, so therefore we need to use this double dot here. So if you write if and you forget this double dots here, well, it's an error bar. It's an error because we don't know what that means. Okay, so apart from that, this statement is actually very similar to C++. And then if we survive all the way up to the end of the for loop, then we return the variable max steps, because it means that this thing is definitely in the Mandelbrot set. Okay, so we finished defining the function, and now we are left with discussing the main part of the code. So there is something which is called underscore name. We're going to return to this later on when we discuss Python implementation, Python details, syntax. But for now, I just want to mention that this is a very useful thing in Fortran, because in Python, because it allows one to test modules. So this is done for testing, and it says that if we are calling this module from the shell, then the name will be the same as main, because somehow when you invoke it through shell, then the name is always equal to main, and therefore all this thing is going to be executed. But if you include this as another module in another as a library in another module, then this part will not be executed. But anyway, now when we call it from the shell, it's going to be executed. So this is going to be executed. But what is that? Well, we specify here nx and ny to be 1000, just like before in other languages. Notice that I didn't create this constant, because as far as I know, Python does not have a concept such as constant, because, well, all the variables are auto-defined. So there is no point of using constants. Yeah, we specified here that maximum steps are 1000, but 1000 take quite a lot of time. I use many times 50 only in Python, because it's kind of in order to speed it up. Then here this array of the minimum and maximum values is xed, as in all languages. And notice in C we had to write double xed, and then brackets, and then specify the initial list, -2, -1, 1, 2, or something like that, 1, 1, whatever. So that's the C-like, and the Python is kind of simpler. So you don't need to specify that x is an array on the left-hand side because it's an auto-type language. So you just need to assign this object array from the right-hand side to a name, x, and this will automatically become an array. Actually, the way Python works is that every variable is actually not a variable. Is you can think of it as really a pointer to something. So in other words, this is going to be stored somewhere in memory, and then this X will point to this memory location. And this could be any type. It could be either a string, it could be array, it could be anything. Okay, but of course we don't think of in terms of pointers when we do Python, but in reality everything is actually a pointer in Python. Yeah. So yes,
I had a question. So if everything's a pointer, if you set like ext equal to some other variable, would they both point to the same place?
No, the nice thing is that it is a pointer. So if you write here below in the next step, ext is equal to 3, then 3 is going to be somewhere else in memory. It's going to be just an integer, and X from now on will point to this other location in memory, to the integer 3. And this xt is going to be lost, and it's going to be somehow deallocated.
Okay, well, let's say you had a different variable, like let's say max steps is also an array, and you set ext, or you set max steps equal to ext. Would max steps then point to the same place as ext points?
Yes. So if I say max steps is equal to ext, you're absolutely right. Both max steps and ext will point in the same direction. This is the same place.
And then if you modify ext, it'll modify max steps as well.
Absolutely, absolutely, absolutely. So, and it's actually, it's one interesting thing about Python is that the arrays and lists behave differently than basic types. So if max steps and X, if both are actually of type integer, then modifying X will not modify max steps, okay? But if the type is list, such as here, -2, -1, and so on, then it will modify. Okay, so it's a bit more complicated. So the way you should think of it is, yes, indeed, everything in Python that is not a simple type is a pointer.
Okay, interesting.
That's how it works. Okay, let's go back. So yeah, so we define this X. Then this T0 here is, of course, the time, which is easy to invoke. So this first time here stands for the module name dot function name, of course, and this gives you a time. I think it's in floating point number. And then this is the statement that that creates a two-dimensional array. So as we know, in Python has this nice NumPy library, which defines very convenient two-dimensional, well, many multi-dimensional arrays, and we're going to use this, of course, with great pleasure. And the way you specify an array and actually both define and initialize is zeros. Zeros means initialize to 0. There is something which is called ones, which means initialize to 1. And there is also a way of specifying calling constructor array, but most of the time I use zeros to set things to 0 at the beginning. And this specifies the dimension, two-dimensional array, and x and y are are the dimensions. And this thing will be called data, will be named data. And again, the same philosophy. This actually is a complicated object or class, and data is just a pointer to this object. Okay, that's how we can think of it if you're advanced in coding in programming languages. Okay, so now here is the double do loop or for loop in Python, and of course nothing surprising here. We go over the range nx or the range of ny. Notice here x is accessed by square brackets. So similar than in C, the lists and arrays use square brackets in Python. And I'm also using here one dot. Okay, it turns out that in Python 3, this one dot is not mandatory anymore. So even if you just use one, it's going to work. But this is only in Python 3. In Python 2, it will be the same issue as in C, namely, this would be evaluating to integer. Now, why did they decide to change that syntax? I don't know. I mean, sometimes we want, in this particular case, we want the result to be proper floating point number, but there are many times when you don't want. And I don't know, now we need to typecast when we don't want. Okay, before we had to typecast when we want. But anyway, you need to be aware of that from Python 2 to Python 3, this conversion of types has changed. Okay, so here we invoke the function that was defined outside. And of course, the entire context of all the libraries and everything is being searched for this variable, for this definition of this function. So, for example, in Fortran, we always need to specify in the new main part of the code that such a function exists. Otherwise, we are not allowed to use it. There is an error. But in Python, of course, the entire context of all the libraries is going to be searched for this symbol and found. So we don't need to specify that this exists. Then here, this is a way of constructing from two floating point numbers a complex number, x plus y times imaginary unit. So 1j is an I in math, isn't that imaginary unit? So this creates a complex number, and then we add max steps. And when the result is being written into the two-dimensional array, notice the two-dimensional array here is square brackets and then comma in between. That means accessing two-dimensional array. And then finally, we will print out. So in this case, we're going to use print statement, which is going to print to the standard output. We could print this also in the standard error output. If we wanted to do that, we will need to specify here. I think you can specify here in Python 3, the way it works is you specify here something which is called file, and then you can give file which is sys stdr. Yeah, I don't have space here, but the way I wanted to write is file stderr, I think. It's a standard error output. So you could specify here, if you wanted to, that this is being written into the error output rather than into the standard output. By default, everything goes to the standard output. But I mean, I don't care right now in Python because we're not gonna print to file. We're gonna actually immediately display the result with imshow. But first, let me cover the print statement. So print statement in Python 3, it's essential to have this square brackets for the print statement. So in Python 2, the square brackets were not needed. Okay, and I'm still very, very used to Python 2, and I always forget square brackets, unfortunately. But in Python 3, they were brought back. So now the print statement actually looks very similar to C-like print statement. C has the same type of print statement, print with brackets. And then inside the brackets, you can have a large number of different types, and you can just comma separate them. Okay, comma separating types. So here is a string, and notice that string with single quotation marks is a string. So in Python, either single or double quotation mark is the same thing, or almost the same thing. So you can specify with single quotation marks, and then here this time is of course the floating point number, which we're gonna this time convert to string by something which is called str. I mean, this conversion to string is not essential. We could just write comma and print out a double number. It would work. I don't know why I decided to convert to string, but this is a way of avoiding, for example, the space. So it turns out that if you print something in Python and you print like string 1, and then you print string 2, it turns out that there is always going to be a space between string 1 and string 2. There's always going to be a space. So if you want to avoid the space somehow, the best way to do it is to concatenate the string. For example, you could do S1 plus S2. This is concatenating. And then with concatenating, it will actually print out S1, S2 together. So if you have this problem that you want to avoid the space, then you use this plus for concatenation. And I don't know why I did it here, because this is not an issue, but it works. It works this way as well, but it's not essential. Okay, so this is the print statement. And then finally, we're going to use imshow. Now, imshow is displaying the two-dimensional array. So if you have a two-dimensional array, such as this, data. So we're going to use 1/data to display, similar than what we did in Fortran. 1/data, basically, this is going to every data point in the array, instead of displaying an integer I, which is max steps, is going to use actually 1/max steps. Okay, so every number in this data is going to be converted into 1 over this number, okay, by the statement. And at the same time, we're going to transpose it, which means that in X direction and Y direction are going to switch, okay? We're going to just transpose the array. Now, why do we transpose the array? Well, because in computer graphics, imshow usually displays things upside down. Okay, the way the arrays are always printed is upside down to what you would expect. So you can try to remove transpose, and you will see that the Mandelbrot set will be kind of pointing upwards or downwards. I think probably downwards. So if you want to avoid that, you need to transpose the array before you display. But the point is that imshow is something that is defined inside pylab. This is matplotlib, and it basically plots any two-dimensional array on computer graphic with every pixel having a color that is proportional to this variable. And this extent here is an option that tells you what are the limits of this plot. So X basically is -2 to 1, -1 to 1, and it will give you correct limits in the plot. Now, by default, this imshow uses some color map, which is pretty decent. If you want to change it, there is an option which is called color map, and you can tune it and change it and have different colors if you want to. But now, and yeah, and once we use any plotting, we need to write some. We need to say something like show. The statement show means everything that was accumulated up to now that has to do with plotting has to be now displayed. So show is something that needs to be done at the end. Now, if I invoke this manp .py, it's unfortunately still much slower than Fortran or C++. So Fortran and C++ were both of the order of 0.2 seconds or something like that, isn't it? While this is expected to be something like 20 seconds. So this is pretty much 100 orders of magnitude. Sorry, 2 orders of magnitude, yeah. So 2 orders of magnitude slower than, so 100 times slower than C++ in Fortran. Well, that's what it is. So if you zoom in, for example, this, you see that it's composed of pixels, isn't it? So it doesn't change dynamically as the other code that we discussed. So the displaying was extremely fast in Python. This displayment, after we saw the clock time thing, displaying was no time, which is nice. So that the plotting is extremely efficient. Unfortunately, the computing is very slow. So these for loops are really slow in Python. That's extremely slow. And well, the subject of the next lecture is going to be how to speed this up. You can easily get 1 order of magnitude in speed by just prepending this numba thing. And you can, of course, gain both orders of magnitude by changing this into C code or something, or a few other tricks. So this is the default implementation, which of course is very, very slow, but there are ways to speeding up Python substantially, and that's what we're gonna do soon. Now, we came to the end of this part, and now I can give you the homework. So we've done this testing. The homework, which some of you have already done, is to set up your environment. So what we discussed up to now, set up your environment, make sure that Python works. Python is most important. If you could get C++ working, would be great. So then you can test these things, and Fortran, G-Fortran, and of course DAS and LAPACK, which is in VClip in Mac. So if you're familiar with coding, you can write your own Mandelbrot version of the code. I mean, I'm not saying in all languages, but at least you can choose one. But this is not essential because I don't expect you to be good enough, to have enough experience to do this quickly. But it's enough to download this code that you did and execute and check that they can be executed and run. And of course, test GNU plot if you can by plotting the Mandelbrot set, and of course testing also in Python that Python matplotlib works properly. So next time we're going to discuss how to improve Python and how to make it fast. Now we are over time. Is there any question from today's lecture? No question. Okay, so I guess see you on Monday. We still have virtual on Monday, as far as I know, isn't it? Yeah, if somebody has a question, you can stay later and ask question. Okay, goodbye.